Inkeraction, an interaction modality powered by ink recognition and synthesis. Digital ink is a powerful medium. It can be used for writing, drawing, and thinking. However, most digital inking tools only have limited abilities to understand and modify ink. Because the inking tools do not fully understand inking input, users are forced to switch between tools and templates to achieve their goal. On the other hand, because the inking tools have limited ink modification capabilities, digital ink is mainly used as an input method, and the inking tools rely on other media to provide output feedback. What if inking tools can better understand and modify digital ink? What can we do with the enhanced ink input and output modalities? To answer these questions, we developed Inkeraction, a new interaction modality that is powered by ink recognition and ink synthesis models. The recognition models segment and classify inking objects like handwriting and sketches and identify the relationships between these objects. The ink synthesis models enable stroke cloning, curve synthesis, and text synthesis in a personalized writing style. In this talk, we will introduce the recognition and synthesis models that power Inkeraction, the design space enabled by Inkeraction, and the user studies we conducted to understand how Inkeraction affects users' inking tasks. We will also share the challenges and suggestions of using Inkeraction. Before we dive into the models, let's step back and think about the inking content. Because users can write and draw a lot of different stuff, inking content tends to be complex and nested. Think about mind maps, doodles, and sketches. They all have connecting and nested inking objects. So one question we need to ask here is, what should we recognize from inking content? For example, how should we teach the algorithms to label a handwriting list? Prior work treated nested inking objects as monolithic entities. For a handwriting list, their algorithms only produce one label, list, which limited the design space for interaction. For example, a user won't be able to interact with items within the list, as we don't know the internal structure of the list. In Inkeraction, we try to preserve nested structures and relationships. For example, our algorithms not only recognize the list, but also the 3 text lines within the list. Moreover, as you can see from the figure, each text line is further annotated with more detailed structures, like bullets and words. This enables us to design interaction with any of these objects. More generally, our algorithms recognize inking content as a relationship graph. On this slide, the inking document on the left is recognized into the relationship graph on the right. Each node in the graph is an inking object, such as text block, list, text line, word, arrow, and bullet. The relationships between these inking objects are described as the connecting edges in the graph, like containing, which are colored in purple, pointing and underlying, which are marked with italic text. To get the relationship graph, our system deploys several graph neural networks to do segmentation and classification. In the segmentation algorithms, initially each stroke is converted into a node embedding. Then, the algorithms identify a fixed number of neighbors for each node. The initial edge embeddings are calculated based on heuristic features such as relative distance and size. The initial GNN, which has the node embeddings and edge embeddings, is updated through several iterations. Then, we identify the nodes that should be merged and merge them into new node embeddings. We repeat this update and merge process several times until there's no more nodes want to merge. Then, we run classification algorithms over the node embeddings to get the labels for the ink objects, such as word. Similarly, an edge between two nodes is classified as a relationship, such as underlying. After creating the GNN for one level, we repeat the process with another set of model weights to create a higher level GNN. For example, the first level GNN merges strokes into words. The second level GNN merges words into text lines. Inkeraction has 3 level GNNs in total. For text objects, we run text recognition to know what the user writes. Additionally, we use character segmentation to understand the text geometrics, like character sizes and word baselines. As for ink output, we implemented 3 methods to handle common use cases. We clone strokes for repetitive items. For example, if a user is moving an item into a list, we clone a bullet for the new list item. We implemented a curve manipulation algorithm to help users redraw connectors and arrows. Lastly, we use a styled synthesizer for text editing and creation. The synthesizer can produce handwriting text mimicking the user's writing style. Stroke cloning and curve manipulation can be achieved with geometric transformations, while the styled synthesizer is implemented through a recurrent neural network model inspired by prior work. I know it's a lot of content to unpack, so let me summarize some key information about the models before we moving forward. First, we use 3 GNNs to recognize an ink document into a hierarchical relationship graph. Second, we have 3 ink synthesis methods. Third, we collected a dataset that has more than 18,000 annotated ink documents. We trained the recognition models on the dataset, and we found its performance was comparable to prior work. Because our models are quite compact, they can run on mobile devices such as tablets. Please refer to the paper for more details. So now we have models that can do ink recognition and ink synthesis, which are basically new ink input and output capabilities. How can these new capabilities enhance inking experience? We explored the design space of Inkeraction in 4 directions. Inkeraction can help users manipulate ink content when they are moving things around. Here, the user is organizing their schedule with 2 lists. They add a swimming session to today's list. Inkeraction aligns it with other list items and clones a bullet for it. Then the user wants to move the piano lesson to tomorrow. Inkeraction rearranges 2 lists and changes the bullets. The user can also mark an item as completed or scribble an item to delete it. Inkeraction can also help users keep track of the relationships between objects. Here, the user manipulates a paragraph with connecting and underlying relationships. After moving the word to a new location, the connector and underline are updated to reflect the relationships. With Inkeraction, digital ink can be edited like typed text, and we can transform features from word processors to digital ink. For example, we can create spell check for handwritten text. Here, the user misspelled immediately. Inkeraction identifies the error and provides a correction suggestion. If the user accepts the correction, Inkeraction will render a handwritten text. Here we show the example of another feature, auto-completion. It predicts the content the user is going to write and renders the prediction in purple strokes. The user can tap on the suggestion to confirm it or simply keep writing to ignore it. Many text formatting features can be applied to handwritten content. For example, we can change a bullet list to a numbered one and adjust the spacing between list items. Inkeraction can also automate tedious writing tasks. When taking notes, we often transcribe content from other sources. Our transcription feature makes this easy. Here, the user drags the information from a website to a list. Our beautification feature allows users to quickly and easily improve the appearance of their handwritten notes. We offer 2 algorithms for beautification. The synthesized algorithm creates new strokes in generic handwritten font. The unsynthesized algorithm preserves the user's personal writing style, but corrects margins and word baselines. Inkeraction provides opportunities for generative models like large language models to assist users directly in inking interfaces. For example, a user can ask an LLM to brainstorm on a list of items. The user can also instruct the LLM to perform a series of written tasks. Additionally, LLM can help the user to organize written content. To understand how Inkeraction would benefit users in inking tasks, we built a prototype on an Android application and conducted 2 user studies. The first study focused on gathering general feedback. 12 participants joined the study. and tried 6 features we showed earlier, and rated the features for learnability, usability, and usefulness. Word processor-inspired features, such as spell check and autocompletion, were rated the most learnable. Beautification and spell check were rated the easiest to use. Assisted manipulation was considered the most useful one. While the results from the first study were insightful, we wanted to further understand how Inkeraction differed from traditional inking tools. The second study had 2 conditions, a baseline condition and an Inkeraction condition. Both of them were on the same Andrii application, but the baseline condition does not have the recognition and synthesis capabilities. 10 participants joined the study. Each participant completed 5 tasks in both conditions. These tasks included things like transcribing a list or rearranging existing strokes. We measured 3 metrics: how many actions each participant performed to complete each task, and the time each participant spent on each task. We also measured the writing qualities with human raters. We found that on average, Inkeraction condition outperformed the baseline across all tasks and metrics. Using Inkeraction, participants used less actions, spent less time, and achieved better writing quality in the tasks. The findings were statistically significant. While the results from both studies were encouraging, we do acknowledge that Inkeraction is not perfect and still has limitations. The recognition results may not always match what the user expects, partially because the recognition algorithms are imperfect and the inking content can also be ambiguous. For example, on this slide, we have a block of written text. It may be 1 paragraph, but can also be a list with 3 lines of items. Our suggestion is to be transparent to users and allow users to preview results. In our prototype, when a user drags an item around, we use a force-directed algorithm to show the recognized structures. When the user hovers the item over a location, we preview the possible outcome for the user. Sometimes it's difficult to interpret user intention. On this slide, there is a list, and the user is moving an item closer to the list. What does the user want here? They might want to push the list away, or they might just want to insert the moving item into the list. To address this challenge, we propose to use micro-interactions to derive the user's desired outcome. We implemented different activation areas, and each activation area represents 1 outcome. The user can move the item to different locations to preview the outcome. Users may want different levels of assistance depending on task and context, and the more help we offer, the more likely users could feel hindered. We suggest that we should allow users to quickly escape unnecessary help. We implemented 2 techniques, unassisted mode and AI undo. In unassisted mode, users can perform actions without any help. To do this, users can use a 2-finger drag gesture to move strokes without assistance. AI undo allows users to cancel some level of help. Here, the user can cancel the bullets through the pop-up option. Our recognition algorithms usually take less than a second on the tablet. However, the user can write much faster. To address this challenge, we suggest avoiding competing with the user. For example, the current auto-completion feature only suggests 1 word, and the user could easily write out the word while waiting for the suggestion. Instead, we can provide longer suggestions, such as a sentence, to offer more benefits to the user. In conclusion, we introduce Inkeraction, an interaction modality with ink input and output capabilities. These capabilities are powered by GNN and RNN models. Inkeraction expands the design space of ink interaction. It can help users manipulate ink objects, transfer word processor features for digital ink, automates tedious writing tasks, and allow users to compose with generative models directly in inking interfaces. Our studies suggested that Inkeraction allowed users to write faster in less steps and achieve better writing quality. As a new interaction modality, Inkeraction also brings new challenges and opportunities. We look forward to future research in this space.